I'm going to talk about checkpointing. Probably a lot of people have heard about it, but it's still, I'm going to explain it a bit. It's just to show the various checkpointing schemes that they are. Checkpointing is a very important step usually in the deployment of AD into a code. So first, I was working before Julia mostly with Fortran and C++. So you come into a code where you praise that you can do AD and the gradient fast, then you butcher the code. Everybody gets maybe a bit, it's annoying that you butcher the code, but you get a fast gradient, and then you run the code, and then the first that you see is that you run out of memory because on a bigger example. And that's because you have to store all these forward states and then do the reverse. So then you have to implement checkpointing into the code, which again adds another layer of complexity. But fortunately, once checkpointing works, people are usually very impressed by the results that you get, because there are really algorithms there that do pretty well. So in a naive so this is going over time-stepping loops, like in the DJ4Earth project. Like you just iterate over a series of time steps. So you go forward and you go reverse. So in order to only use, to trace only one single time step, what you could do is store every time step and then restore every time step, compute the adjoint of that time step, then use that to initialize the reverse run of the next checkpoint that you're going to restore. So then you have already much less memory used for the trace, but you still use a lot for the checkpointing then, and it will still bite you because it uses too much. And you cannot do these shiny simulations that Krishna did with Psychopolis AD with long time spans to do climate simulations.
Look at me.
Yeah?
Otherwise the camera just
Oh, okay. Boy. So.
Not that back.
Okay.
Give it a second.
Oh, I think I moved a bit and then it. Okay.
Don't move.
Don't move. Don't move. Look.
What you can do is step on the other side.
Yeah, but who pushes the button? Thank you. So our goals were then setting out. Julia now enables us to really leverage the language and not do it the Fortran C++ way, because you have code reflection through the macros. You can actually change the code at runtime. So you don't need to be invasive in the code. You can maybe create a small macro that changes the code in such a way that it does checkpointing AD and everything. And the developer, the application developer, still sees his original code and doesn't have to bother. So that was our main goal. And it should be fully automated. So usually checkpointing requires, Laurent went into it this morning, you have to determine which values you want to store, which you don't want to store. We ignore that and store everything now for the time being, since we assume that most of the model that most of the variables are involved and are actually active in the differentiation. That may not be true, of course, for some applications. And we want to support various storage devices. So you may want to store to disk, to RAM, etc. And all of that in a non-invasive way. Next slide, please. So here's, for instance, a checkpointing scheme, periodic one, where you just periodically, every 2 time step, you store. So you use less memory already, like half, but you still store a lot, and then you reverse and compute the adjoint, etc., and you walk back. So, and Andreas Skrivank, he came up with the binomial checkpointing, which still to this day is pretty impressive, I think. So it places the checkpoints, you give it a number of checkpoints that it has available, and first it uses all the checkpoints in running forward and places them in such a way that it can use them optimally. Especially during the reverse run, it will reuse the checkpoints that have been freed by already being done with the reverse run up to a point. So it will reuse those checkpoints and have more checkpoints available the more to the end it comes. So that's actually very neat. And when you then see 10,000 time steps, so with you would usually use 10,000 checkpoints if you want to have no slowdown, right? Just do forward and reverse and do the trace of one single time step, or have, of course, store the anti-trace. But let's say you only use 7 checkpoints, then you have a slowdown factor of 7, which I find just always impressive when you look at it. You do 10,000 time steps, you only have 7 checkpoints, and you can then get only a slowdown of 7, and you only need to store the trace of one single checkpoint. So that's a huge saving in memory. Next slide, please. So then next step was, Krishna was, I think this was his first project with Julia, and he was also like very, yay, things are getting simpler. So here's my Fortran code. Let's try to run it, and it did not work. Because all AD tools at that time, when we started the project, were not aware of Enzyme, at least at the start, were not supporting mutation. So you cannot change an entry in an array and then assign it. No, you can actually read it, but you cannot write it to a single entry in an array. So it would not automatically store these intermediate values. And so this was OK. So we had to rewrite. And then you get also allocations in the code. It's not how you usually write numerical simulation codes. It's how ML codes are, or these frameworks tend to be written. But it's not how you usually write. You do in-place array manipulation. Next slide, please. So, yeah. So that was the first observation. We need mutation. Second observation is that usually the code has a loop. And then inside the loop, there's an object. Yeah, here one sees it better, like domain or the sim or the model, whatever, where it iterates over. And in that object, in Julia, you then have that's a struct then, and you have all your variables and everything in there. So it sounds pretty easy to capture that and just store everything of that struct. And that's effectively what we do. Yeah, it overestimates, but it's already, but you can deploy it faster. So you are at least fast in a state where you use less memory and can do first runs with a lot of time steps. Next slide, please. Yeah, so support loops with structs, mutation aware AD tools. So we ended up with Billy and Valentin. So we needed Enzyme for the inner part of the loop. And so adjoint checkpointing, how do we embed that then? And there's also a nice idea I really like about Julia. That's the package chainrules.jl. The idea is that you can define custom chain rules once, and it's like a library, like a big library of all differentiation rules that exists. And you pick out the rules that you want, and it will use them in your code independent of the AD tool that you're using, because the AD tools will all use that same library. That's the idea. But on top of that, that you have this unified place where numerics people can put in their specialized AD rules of iterative solvers, etc., that are really difficult, that you do not want to come up with yourself or run into the mistakes that you can do. You can then just use these rules. But on top of that, what it has is that you can define, you load your package, and independent of the content of chain rules, you can add your own chain rule globally. So that's what Julia, that is what's so nice about Julia. Some don't like it because you then don't see what is happening in the code, but you can essentially just create your own differentiation rules. And that's essentially, so we just treat checkpointing as just another function. And so it will be a function in the code, a loop function. A loop is essentially just a function that you need to adjoin. And that's all. So you create a custom rule for loops, and that's it. You have an adjoint. And every AD tool should be able to capture it. Yeah, next slide. So this was the current status, and probably I updated. Yeah, so yeah, we made it. It's available. You can use it in Julia. You can do add checkpointing, but I would expect it to break. We have tests though, a few, so it should be. But it's so we have implemented revolve for a fixed number of total time steps. It will essentially give you The revolve scheme, which I showed, is this binomial checkpointing, which is very nice. And then periodic. Periodic is still needed if you write. So revolve assumes that the read and write to memory have no cost in the theory. So it's only optimal if you can read very fast to memory and back, which is the case in RAM, for instance, but not to a disk. So periodic checkpointing, for instance, still makes sense if you want to stream out data to a disk all the time while going forward. Then you would just periodically put your checkpoint, as many checkpoints as you can effectively, and not use revolve, for instance. Online revolve is important because you have an unknown number of time steps. So there was some work done to implement online, which is then called online revolve. And then we support just the array type, which is essentially storing to RAM, and HDF5, which gives us, especially on the machines, a clear interface how to write to disk. And you can write to the on-node SSD disk, to the archive if you want to. So it gives us a lot of flexibility of how you want to write your file to disk. So that covers us well. Yeah, so and then we also are able to use a different AD tool on the outside than on the inside. So you are, if you have mutation, well, actually it doesn't matter, but you can use an AD tool on the outside and an AD tool on the inside of your time loop, and those can be different. And that's also often the case because usually the AD tools that deliver very high performance are not generic, and those which are generic do not deliver high performance. So that's how it used to be in general. And so you want for your outer code where you set up everything, you may want to use an AD tool where the goal is to get through. And then you come to the high performing part, and then you want to use really something like Enzyme, or as generic also as Enzyme, so and use the really high performing part, do the high performing part. Okay, next one. So here's the work we did with Sarah, and so she kept an eye on that we were presenting it correctly and helped us in implementing this. So Burger's equation, the simplest non-linear equation where you need to do checkpointing in order to integrate it over time if you want to have adjoint sensitivity. So here you see the initial state, then the final state after a certain number of time steps. Then we compute the energy of the final field, and we compute the sensitivity of that final energy with respect to the initial conditions in both directions. So, and this is then the field we end up with, which just, yeah, looks funny, as like this, yeah. Okay, and so checkpointing.jl. So here's the energy function, and here's the loop, the time loop. And then we do just the sum, so compute the energy. And you see then here, for instance, a all reduce popping up. Now the outside of the code, we actually, so for this we use then, for the inside loop we use Enzyme. For the outside we use Zygote. Zygote cannot do MPI, Enzyme can do MPI. So for the MPI all reduce, we just defined an adjoint using chain rules for our code, for the reduction that we need. You just put it in and it runs. So that's actually, again, the flexibility of chain rules and why I do like it. If something breaks and there's no rule, you can just put it there and maybe hope it will work, and it does, for instance, work for an MPI reduction here. So this is then the outside code, the driver code. You create your checkpointing object, where you say what object is being checkpointed, how many time steps, number of snapshots, where you want to store it, and yeah, boundary conditions, initial conditions, and then you just call Zygote gradient, your ID tool's API, to computing the gradient, and everything happens. You don't have to do anything else. Yeah, and then the loop is decorated with this decorator with the scheme, and the object has to be passed. Okay. Yeah, here then all the, again, 3 different schemes that you can specify. Yeah, this is again repetition, exactly. Why did I do? I wanted to say more, but probably. Storage, yeah, the storage can then be, since I didn't have that on the previous slide, the storage then can be either array storage or HDF5. Here's an example with HDF5. So number of snapshots, I think it will just use a default file name, but you can also specify a file name. Yeah, conclusions and outlook. So the shadow abstraction of enzyme really fits well, I think, for what we are doing and numerical simulation codes. Then a differentiation rules system like chain rules is really also very powerful and allowed us to implement this. So we essentially relied on the shoulders of giants or whatever. We relied on other people who had these great ideas so that we could implement it that simply. And as Valentin put it, write a paper about a single macro. And so add support for enzyme custom rules. So that is done now, as was presented, and I just need to add it, and it's on me to add it to checkpointing.jl. That's it, I think. Oh, yeah, I think there's nothing else, right? Oh. No. Oh, implicit time steppers. Yeah, that's also something that I thought about while being here. Right, when you have implicit time steppers, because then you don't have the same number of time steps going forward and reverse. You may want to interpolate. You may want to do all sorts of stuff to do the reverse. Yeah, now I'm done.
Do you have any questions for Michel? Okay.
So my question is about, like, what is our strategy for observability? So we've got, like, checkpointing is something that we need semantically in order to evaluate the adjoint equations. But in practice, we want diagnostics. In fact, one of the distinguishing features between a kind of toy solver and a production solver is that you're going to have all kinds of rich diagnostics that are available, possibly that you can switch on and off dynamically while a simulation executes in your production code. And so, like, what is our strategy? Do we put a lot of hooks in and write kind of outputs that, due to configuration, are silent by default, and all of those outputs have like custom gradients that are then output hooks that might be turned on for the adjoint equation?
Yeah.
Or is there a different strategy?
I mean, I definitely, I'm. So yeah, we had the discussion also before about the Krylov solvers implemented in Julia, and in a way it also goes back to debugging adjoint code. Like how much does the developer, the user, want to be exposed to the complexities? And I think that's a debate that is probably never going to end. We have verbose 0, 1, 2, 3, and then you can get the checkpointing output, like what is going on. But I think that's in general the problem about Julia, definitely, about observability. Like how do you make the user aware of? I don't have an answer for it, definitely.
Thanks. I may have missed it or misinterpreted it. Are you also looking at adjoint dump and restart? Is that what you meant by the adjoint checkpointing? Or so what we want to do is we want to actually interrupt the adjoint calculation and then restart it. Is that?
You mean stopping the entire code and restart?
Yes. So we want to.
That would have to be integrated into the application code, but I think a similar strategy. I'm actually wondering whether this could be extended to a general checkpointing in the sense of restart.
Exactly.
Checkpointing.
I mean, so if you think about big production codes,
yes,
they
yes,
will
yes.
run, an HPC
again,
center will tell you 12-hour run sort of queue limit, and so you have to, during your adjoint sort of sweep, right? So you have to basically also dump the adjoint state itself and then pick up the adjoints.
Well, if you use HDF5, you have it there. While it goes, you will have constantly the state of the adjoint, and I mean, I think you can recover then from a certain step, right? Okay. Oh, but I should also write out the adjoints. That's what you're saying. Yes. Okay. Yeah. Yeah. I can dump the adjoints, definitely. That's easy. But still, this has also a very strong constraint on that the user has this struct, has stored everything in it. It does not do any automatic detection, right, of the variables, the required variables.
So a lot of numerical simulations have stochasticity involved, so they'll have some random numbers generated at some point. Is there an intelligent way that checkpointing can deal with this? I mean, I guess the way that springs to mind is you just store some random seed with the simulation state, and then you just regenerate based on
I think that's also a great case for the chain rules. Just, I mean, I guess that's a whole field in itself, how you should do the randomness. Usually, I mean, naively, I would of course just try to record the forward random whatever was generated and use it on the reverse. But that may not be enough, right? So I don't know. But that's, again, you can use chain rules or JL and reverse your random call if you.
I have a point to Pat's question earlier, well, around checkpointing and restarting a Julia program. The biggest challenge with that is that the state of the runtime, which includes all of the defined methods, is not going to be checkpointed. When you restart, you will need to be able to restart to a point where the metadata of the program, essentially the program definition, is exactly the same as before. This can already cause you fun issues if you're in a distributed environment and the root processor loads a different file than all of the other processes and loads a different package that adds a different method, and suddenly you have sliding consistencies between the root 0 and all of the other processes, which is not fun. And so that's, I think, one of the biggest challenges is be able to do restarting of Julia programs, is to figure out how can we actually snapshot that global state. That is, as Michel said, it's not captured by checkpointing right now because he's only concerned about the data, not the programming.
That's a Julia issue more than an enzyme or any other issue.
But it shouldn't also code that, yeah. That's
People. That's why code.